The Kansas City Royals in the last 10 games have an 8-2 record, which is very, very good. I want to know what the Kansas City Royals, who are on a roll right now, have in common with this train that's moving down the tracks. They both have? Good. They both have momentum. What does momentum mean? Define momentum for me. How can the Kansas City Royals, a sports team, have momentum, same as a train has momentum when it's moving down the tracks? Define momentum for me. Go ahead, Matt. Okay, an object that's in motion, wanting to stay in motion, kind of, yeah. Newton's first law, the law of inertia, momentum and inertia are not the same thing, as you're going to see in a moment, but they're similar to each other. Here's the way I think of momentum. This is not a technical definition of momentum, but it's a good way to think of it. Momentum is how hard it is to stop something. Is it hard to stop a team that's 8-2 in the last 10 games? Yeah, it is. It's intimidating. When you go in to play them, it's intimidating because all they do is win. It's hard to stop them when they're on a roll like that. Is it hard to stop a train? Yeah, it's hard to stop a train. Don't try it. These two things, the sports team that has an 8-2 record, the train moving down the tracks, are both hard to stop. They both have momentum. This momentum that a sports team would have would be more of a psychological momentum, though, as opposed to a physical momentum. It is hard to stop them, but there's no real good reason why it's hard to stop them. Like objectively, you should be able to beat a team that's 8-2. But there's something psychological that keeps us oftentimes from beating that team, from stopping that team. It's hard to stop them psychologically. This one, it's hard to stop physically. And that's what we want to focus on in Physics 30, of course, is momentum, how hard it is to stop something physically, not psychologically. Answer this for me. If we're looking at this train having momentum, being difficult to stop, can you tell me what two factors would make this train difficult to stop? We're not talking about the sports team anymore, right? We're not talking about psychological momentum, but rather now we're talking about the physical momentum entirely. Speed or velocity? Yeah. Okay, the faster something's moving, the harder it is to stop, right? And one more, Ian? Mass. Trains are heavy. Right? Sometimes they're moving fast as well, but they're always heavy. They're hard to stop mainly because they're heavy. Sometimes they're hard to stop because they're moving fast. Sometimes they're hard to stop because of both. Momentum is how hard it is to stop something, but the real technical definition is the product of mass and velocity, because it's the mass and velocity that makes something hard to stop. A number of years ago, I was sitting at the tracks, the train crossing by the town office in Okotoks there. There was a train coming. I hadn't crossed the tracks, the crossing yet, but it was coming. It was dark, and I saw it coming from a ways away. I stopped. The lights are going. Okay, I stopped. And then I decided, you know what, I don't want to wait. I don't want to wait for that train because trains in Okotoks are long, and I'm going to be sitting there for 5 or 10 minutes. So I decided to turn down that alleyway behind the town office, and I do. And as I do that, as I turn down that alleyway, the train goes by, like right beside me. Okay, then I turn around, I go to a little store, pick up a snack, and then I said, oh, the train's got to be gone by now after I'm out of the store. So I come back around to go across the crossing again, and the train has stopped right on the crossing. I look to my left down the track. There's a van that just got T-boned by this train and is now 300 meters down the track, 3 football fields down the track. So this train that was coming, that I turned and decided to skip, it literally hit the van that was behind me in line at the tracks, and I didn't even know it until after it got hit and the train was stopped. Why was it 300 meters down the track? Why did the train not stop immediately? Why did the train not stop before it hit the van? You got to figure the driver, the engineer on the train saw the van there. Why didn't it just stop? It's hard to stop a train. And why is it hard to stop a train? Because it has a lot of mass. It has a lot of momentum, and it has a lot of momentum because it has a lot of mass. Okay? What else is hard to stop? A bullet's hard to stop. Don't try to stop one of those either. Why is a bullet hard to stop? Doesn't weigh hardly anything. Because it's got a lot of velocity. So something can be hard to stop because it has a lot of mass and or because it has a lot of velocity. Momentum is the combination, the product of that mass and velocity. Versus inertia. Somebody mentioned object in motion. Matt, was it you? Okay, Newton's first law, the law of inertia. So it's kind of tied in here. Not exactly the same thing. Momentum is how hard it is to stop something versus inertia, which is how hard it is to change the motion of something. What's the difference? It sounds a lot the same. Well, here's the difference. The train, as it was moving down the track that night in Okotoks a number of years ago, had momentum. It was difficult to stop that train. It also had a lot of inertia. It was hard to change the motion of that train. That train, once it was stopped after it T-boned that van, had no momentum. It wasn't hard to stop the train because it was already stopped. Was it hard to change the motion of the train? The train is stopped, but it still has a lot of inertia. It has no momentum anymore, but it still has inertia. So inertia is how hard it is to change the motion in general, and it depends not on mass and velocity, but rather what? Inertia depends upon just mass. Doesn't matter how fast it's going. A train is hard to change the motion. It's hard to change the motion of a train, regardless of whether the train is moving at 100 kilometers an hour or 0. It's hard to change its motion. Right? This train is moving down the tracks. This train is at rest at the train station. Which one has inertia? Which one has inertia? Train 1 or train 2? Train 2 has inertia. Yep. Because it's hard to change the motion of that train. Does train 1 have inertia? Yeah, because it's hard to change the motion of that train. Which one has momentum? Train 1, because it's the one that's moving. This one has momentum. This one does not have momentum because it doesn't have velocity. Does that make sense? Good. We're going to focus on momentum this unit, not so much inertia. I just want you to know the difference. Momentum is a vector. It's directionally dependent. If the velocity of a train is to the east, then the momentum of a train is to the east. If the velocity of a baseball is 60 degrees south of west, then the momentum of the baseball is 60 degrees south of west. Whatever the direction of the velocity, that's the direction of the momentum. And finally, an equation, which, as much as I told you earlier, you got to think a lot more in physics 30 than you do in physics 20. It's not just equations and recipes like it is in physics 20. There's still a lot of equations. And here's the first one. Symbol for momentum is a lowercase p. Not a capital, that would be power. It's a lowercase p. And there's a little half arrow over top of it because that's indicating that it's a vector. What do you think it's equal to? You know this, right? Mass times velocity, right? It's the definition of momentum, mass times velocity. What units do we typically use for mass? Kilograms are the standard units, yeah. I mean, there's times when we use something else, but the standard units would be kilograms. What about velocity? Stefan, what units would we use for velocity typically? Good. All right, what do you think the units for momentum are then? Who said that? Good. Kilograms times meters per second. If we were talking about energy, the units would be kilograms times meters squared per second squared. And we can we can kind of shorten that into a nice tidy unit called a joule. We can't shorten this one. Okay, it is what it is. It's kilogram meters per second. There's nothing shorter, no more convenient unit like a joule that we have for momentum. This is it. We got an example for you here. It says a 180 kilogram bumper car carrying a 70 kilogram driver has a constant velocity of 3 meters per second to the east. What's the momentum of the car driver's system? And draw the velocity vector and the momentum vector. We're not going to worry so much about that. In fact, we'll cross that off. What's the momentum of the car driver system? Hey, what's the big thing you got to watch out for here? It's not a hard thing, but it's something if you're not careful, you can miss it pretty easily. Units, sure. Units are always an issue for us. For sure, we've always got to pay attention to that, Riley. What about the mass? Yeah, we got to add the two, right? Like, given enough time and paying enough attention, all of us would get that, right? All of us would get that. It's not that hard. But if you're not paying attention or you're just trying to do it too quick, we might miss that. Our mass is not 180 or 70. Our mass is 250 kilograms. Our velocity is 3 meters per second. I'm going to define east as positive, so plus 3 means 3 to the east. And I want to find the momentum. Now I think you're going to find it's a pretty straightforward question at this point. Mass is 250 times 3.0. What does that give us? 750. How would I express that? Yeah, units, yeah, but what about the number? Jack? Good. 7.5 times 10 to the 2. And Connor said kilograms meters per second there. Jack, why 7.5 as opposed to 750? Yeah, right. We got to look at our least precise piece of data, and our final answer has to be that number of significant figures, 2 significant figures. Good? We got a positive value, and we know that positive means east, so it means 757.5 times 10 to the 2 to the east. Good? Listen, I don't care if the direction is to the east or to the west or to the south or to the north or west of north or south of west. You want to find the momentum. It's defined as mass times velocity. Multiply the mass times velocity. And whatever direction the velocity is in, that's going to be the direction of the momentum as well. Sometimes it's not going to be quite as neat and tidy as this to the east. Sometimes it's going to be a little bit messier like this, where you've got 60 degrees north of east. Doesn't change a thing. Okay, it doesn't change a thing. The momentum is in the same direction as the velocity. Okay, take a look at these two questions, please, on page 451 minus question 1b. Guys, let's have a look at question number 1. There's one thing in particular that I want to point out with this. Okay, we know that the momentum is the same direction as the velocity. So what we're going to do here is multiply the mass times the velocity, right? 600 kilograms times 11.5 at 60 degrees north of east. And when we do that, we end up getting this number with this direction. But the one thing that I want to draw to your attention here is the significant figures. Okay, I know there was at least one person, I suspect it was more than this, that had a little bit of an issue with this. They looked at this and said, look, shouldn't it be 2 significant figures? 2 digits, 3 digits, 3 digits, and we use this one, so the final answer should be 2 digits, right? Anybody else kind of have that thought? Here's the thing. This relies on a rule that we often don't teach in Physics 20 because it's such a rarity that it actually appears. There are actually 2 rules for calculating significant figures. The first rule is for multiplication and division, which is the rule that we always teach you because that's the one that you use far and away the most often. It's rare that you get a question in Physics 30 or Physics 20 that doesn't involve multiplication or division, right? But there's also a rule for addition and subtraction. The rule for multiplication and division is, look, just count up the number of digits. 2 digits, 3 digits, 3 digits, final answer should be 2 digits. But the rule for addition and subtraction is not count the significant figures, count the decimal places. So when we're adding these two numbers together, 65 plus 535, the answer is not 6.0 times 10 to the 2. The answer is 600. We're not counting up the number of significant figures, 2 digits, 3 digits. We're counting up the decimal places. 0 decimal places here. 0 decimal places here. Final answer for the addition should be 0 decimal places. And then, what are we doing? We're multiplying 600 with 3 digits by 11.5 with 3 digits. Does that make sense? You know what? Honestly, that's probably the last time you're going to see that. I mean, it just doesn't happen. You get a problem that involves addition that's going to throw a wrench into things like that. The other thing is, good news, okay, on your unit tests, we always tell you, round and record your answer to 3 digits or 2 digits or 4 digits. We tell you that because it's a numerical response type thing, so you have to fill it into the right number of digits, okay? Yep. Yeah, and numeric response, yeah. Yeah. For tests, lots of it will, but not all, no. Yep, yeah. Okay, I got one more for you, and then we're going to end it there. This is one that you're unfortunately going to have to copy out because it doesn't appear in your textbook. It says a 1.5 kilogram object falls from a height of 14 meters. What's the momentum of the object as it hits the ground? When you read this question, tell me what's similar about this question as compared to the last example we did. What does this question have in common with the first example that we did in Physics 30, Connor? No? I mean, we're not looking to overanalyze this, okay? We're looking for momentum, yeah. Momentum is a quantity that exists at a specific moment in time. We want to find the momentum of an object at a certain moment in time. Okay, same as the other question. What's different about this question? Okay, it doesn't have velocity, sure. It doesn't have velocity. Right? It's going down, so the velocity is changing. The last example, the velocity was staying the same, right? So here's what we got to be careful of here. We need a velocity, clearly. We need a velocity. But we don't just need any velocity. In the last question we did, the velocity wasn't changing. So wherever we had it, it didn't really matter because it was the same. But in this question, the velocity is changing. We need to make sure we use the right velocity. If we want to find the momentum as it hits the ground, we need the velocity as it hits the ground. So let's get that. Let's write down some givens, and then let's get the velocity as it strikes the ground. My mass here is 1.5 kilograms. What do you want to call this? 14 meters. What variable do you want to call that? I heard somebody kind of whisper. Ethan? What did you say? That? Distance or displacement? Let's make it negative 14, actually. How come negative 14? Because it's going down, right? We want to find the final momentum. Oh, VI is 0, right? Because it's dropped, so it starts at rest. We want to find the final momentum, the momentum as it strikes the ground. So let's find the final momentum by multiplying m times the final velocity. But we need to find the final velocity. Suggestion? We got a physics 20 problem now. Yeah, right? Sure. VF squared is equal to VI squared plus 2AD. That works, I think. VF is going to be equal to the square root of 0 squared plus 2 times neg 9.81 times negative 14. Do the math there. It works out to be 16.5734 meters per second. Plug those numbers in. 1.50 for the mass, 16.5734 for the velocity, and we get 24.9 kilograms meters per second, right? Right? Not quite. There's a small error there. It's a really small error, but it's an error nonetheless. Yep. Yeah. What do we find right here, Riley? What did we solve for right there? Nope. Close. We didn't solve for the final velocity there. We solved for the final speed, which is a scalar. But when we plug that into here, we need final velocity. It was a downward velocity, so a negative velocity. That means our momentum is negative 24.9, or you could have just said 24.9 downwards, right? Negative or downwards, either one. Yep. Yeah, you could have said down is positive, sure. If we don't say anything, we're going to assume that though that down is negative, right?